Good morning, everyone. This is the first segment for section 4.1. This is the first video for chapter 4. And what I would like to do is just take a minute to express some big ideas for this chapter. This tends to be a fairly challenging chapter for most students, so I'm going to try to do my best to sort of break it down into the really critical components of this exercise. What I have noticed about the way the textbook is set up is that there's this expectation that that at the end of it you should be able to both draw or graph all of the basic six trig functions, but also be able to translate and transform them as well. But unfortunately, the way the textbook sets this up is it shows you the two most important functions right off the bat, and then waits until later to actually talk about how to translate and transform them. In addition to that, it very rarely gives you a situation where there's more than two things going on at one time. So just to be clear, there are two kinds of translations. There are two types of transformations. And generally speaking, those are, at least in this textbook, are given some standard letters that are associated with those sorts of things. So before we go anywhere into the material for this section, I want to give sort of a brief overview of some things that probably should be pretty familiar if you did well in like a college algebra class in the graphing section, which to be completely frank, a lot of people don't do really well with that material because it is very confusing. So I'm going to kick it over here to the document camera, and we're gonna get started with some basic concepts, and we'll see where we get. I think this is really kind of a long section because it sets up a lot of things. So I will try to keep it to around 20 minutes, but we may have to break it up sort of strangely. So this is section 4.1, and this is the first page. Okay, so let's just start with a big idea. What we're looking at is suppose you have a graph of some particular function. We'll call that function f. So y equals f of x. This should look like familiar notation from college algebra. So supposing that the graph of f of x looks something like this. Let's just kind of throw in a little swoosh there, maybe something like that. And we're not really too concerned about what happens on the far end. We just need enough of this graph to sort of look at. So when you did this in college algebra, what you looked at was two kinds of translations, two types of transformations. And what this, in a symbolic representation, you would have an equation that looked like y equal a times f of b of x minus c plus d. Okay, so we have four different parameters, a, b, c, and d. And these will do things to this graph that they'll stretch it, they'll shrink it, they'll move it up and down, left and right. And we want to be able to describe that in a general sense using just a generic function. And then when it comes time, we're going to do that with our trigonometric functions. There's also some other stuff that we want to talk about along the way. But I want to kind of set up this idea. So first off, I'm going to define what each one of these is called. So A is what's called the vertical stretch or shrink. And I'm going to use that in quotations because that's not a technical term. Stretch or shrink. And basically what this quantity does is as A gets, I should also say if A is less than 0, that is to say if it's negative, this is a flip. Or a reflection. So if you have a negative quantity here, it will take this graph and just mirror image it across the x-axis. So that's what A is. It's this vertical stretch shrink, which you probably recall from college algebra. What about B? Well, B happens to be a horizontal stretch and shrink. Stretch or, depends on the magnitude. And just like A, if B is less than 0, this is a flipper reflection. But for the time being, I will tell you this: when it comes to trig functions, we will try to always get rid of this a negative sign on the B, because it's easy to do, simply because these trig functions are what are called odd or even, which we haven't gotten to yet. But recognize that if this is a negative quantity, it will cause this this graph not to reflect over the x-axis, but actually across the y-axis. But like I said, we'll try to get rid of that. And there are ways to do it. So when we get to that, I'll kind of point that out. Now, C is what's called a horizontal shift. And what that means is if C is, and notice there's a negative sign here. That's kind of critical, because the negative, if C is a positive number, then this whole quantity is negative, but that represents a shift in the positive x direction. So if C is a positive number, then this whole graph kind of shifts to the right. If C is a negative number, it shifts to the left. And this is kind of backwards from what's intuitive. That's why there's a negative sign there. So x minus 2, for example, would push this thing 2 units to the right. You'd take the whole graph and shift it to the right. D is called the vertical shift. And the vertical shift is really just takes the whole graph and translates it up or down. If D is positive, it shifts it up. If D is negative, it shifts it down. This one is probably, the vertical shift is probably the easiest one to understand. The horizontal shift is kind of a little bit tricky because it sits inside of that parentheses. It's really the transformations that are the hardest for, in my experiences, for students to really be able to master. So I'm going to try to also introduce this idea of what's called periodicity. Every trig function is periodic, which will help us when we try to graph these. At some point, as x increases, as the argument increases, you end up at a point where the graph repeats itself. And so let me kind of introduce this idea here formally. So let's see, section 4.1, page 2 now. Okay, so I'm going to make a definition here. So this is a definition of a periodic function, and I'm going to name the function f, is any function where f of x is equal to f of x plus n times p, where p is a fixed real number and n is an integer. So what is that saying? Specifically, and I have to be a little careful here because sometimes this is used to represent, maybe a double period or whatever else. But what we need to be careful is to say that also P is the least positive value for which the equation holds. And furthermore, in this context, P is called the period. So there's kind of two definitions buried in there, periodic function. And let me just try to take a minute to explain what this is saying. So let's suppose that we do have a periodic function, whatever it happens to be, and the period is like 1, let's say. So what this is saying is that for any value of x, no matter what it is, that x is, f of x is actually equal to f of x plus 1. That would be where n is equal to 1. It's also equal to f of x plus 2, f of x plus 3, f of x plus 4. So you have this sequence of positions on the x-axis where the graph repeats itself. The reason that we call this the period when it's the least value is because you could certainly have a situation where twice the period would do the same thing. So we kind of preferentially choose the smallest value for which this works, and we want to make it positive so we don't confuse the issue. N is allowed to be positive and negative. Just as a reminder, an integer is a quote whole number, negative, positive, or 0. So obviously it's true if n is equal to 0 because you just have f of x equal to x, f of x. But when you do actually have a periodic function, it will repeat over and over and over again. So just as let's see, just as kind of a setup with these two different ideas, I want to start by noting that every trigonometric function is periodic. And a lot of our exercises will involve trying to find this period because this period is directly related to that horizontal stretch and shrink that I mentioned previously, the quantity B. Okay, so let's do a little exercise here. We're going to focus on, I mean, we've kind of had these big picture ideas, but let's focus on some specific functions. So let's consider sine and cosine. Now, in order to do this, I'm going to approximate some values. So section 4.1, page 3. So let's consider, if you don't know how to graph a function, you may recall that, back in algebra class, probably years ago, you would create a sort of a point table. You plug in certain values of x and you get certain values of y out of it. So let's consider the function y equal sine of x. And we don't know all the values of sine for a given value of x. We don't know all of them. We can use a calculator, but let's use the ones that we actually know. So I'm going to create this point table. So x sine of x. So for 0, sine of 0 is equal to 0. And I'm going to do this in radians because we do know what radians are, so we might as well start using those. So the very next value of x that we have a known value of sine of x is pi over 6. And at pi over 6, we know that sine is equal to 1/2. I'm going to put it in decimal because we're eventually going to graph this. So at pi over 6, the value is 0.5. Now at the next value that we have is pi over 4. That's a 45-degree angle. And at this value, it's sine of pi over 4 is root 2 over 2. And if you've ever played around with your calculator on this, you'll know that that happens to be approximately equal to 0.71. Okay. The next known value happens at pi over 3. And at pi over 3, again, this is sine of a 60-degree angle. We know that that's square root of 3 over 2. If you approximate this, it's about 0.87. Okay, and then finally, extend my point table here a little bit. Pi over 2 you get a value of 1, and that is exact. Okay, so we have some exact values and some that are approximate. But in order to graph it, we'll use the approximations. We can't really tell much difference anyways. So as we move into this is our quadrant 1, known quadrant 1 angles. What happens as we move into quadrant 2? Well, the next value is 2 pi over 3, and this is again square root of 3 over 2. So it has the same value, 0.87. And then we have the next one will be 3 pi over 4, which again has this value of 0.71. The next known quantity is 5 pi over 6, which has a value of 0.5. And then finally, we get to pi. And pi has a sine of pi is a value of 0. Now, at this point, you can see that it has kind of gone up and then gone down, right? What happens in quadrant 2 is that we have an exact repetition of this, except that all the signs are reversed, right? The SIGNs are reversed. So for example, 7 pi over 6, quadrant 3 angle, reference angle of pi over 6, has a numerical value of negative 0.5. And then at 5 pi over 4, again, it's quadrant 3, so it has a negative SIGN, but the reference angle is pi over 4, and so the value is negative 0.71. So you can kind of see that this starts to repeat, but in the negative, right? So where does that stop? Well, it goes through this cycle where at pi it's 0, it has a couple of negative values, and then if we just kind of ... sort of fill this in, at 2 pi, we're back to 0. Okay, so I'll just kind of put some negative values between pi and 2 pi, because sine is negative in both quadrant 3 and quadrant 4, but it's these exact numbers, right? So it'd be negative 1/2, negative 0.71, negative 0.87, negative 1, that's at 3 pi over 2, etc. So notice, once we get to 2 pi, the whole cycle repeats itself, right? And so for this particular case, and it just does that over and over and over again. This is the whole idea of a coterminal angle. So just from this sort of inspection, we can basically make the statement that this is equal to p for the function sine, right? And thus we can create this sort of equation: sine of x is equal to sine of x plus 2 pi times n. And I kind of reversed this. This is our p value, and that's our n, where n is some integer. And that's the symbol for integers, that bold Z, which I think you may have seen before. Okay, so now that we have those values, let's try to graph the thing and see what it looks like. Section 4.1, now we're on page 3, yeah, page 3, okay. Sorry, that's page 4. Okay, so I'm gonna just start by graphing. I'm gonna try to be really careful. It's hard to graph without some graph paper, but I think I can do a decent enough job. So I'm gonna start just with positive angles. So this will be my y-axis, and here's my x-axis. Now what I'd like to do is I'd like to go through a total x from 0 to 2 pi. So I'll make this 2 pi. And this is sort of the secret to dividing up these graphs, is to kind of keep splitting them. So if this is 2 pi, then halfway between that is pi, and halfway between that is pi over 2. 3 pi over 2. And then between these, we have halves and thirds. So your thirds are 1, 2, 1, 2, 1, 2, 1, 2. Those are representing, like this one is pi over 6. This is pi over 3, 2 pi over 3. I'm not going to write them all in there because it starts to make a mess. But right here we have pi over 4. And here's 3 pi over 4, 5 pi over 4. I'm just basically splitting these, and then 7 pi over 4. All right, so notice that none of those values exceed 1 or negative 1. So I'm just going to kind of label here negative 1 and 1. All right, so going back to my table of values, now I'll just start graphing points. So remember, sine of 0 was 0, so the origin is part of this graph. Remember at pi over 3, it was half. So we've got a point basically right about here. For pi over 4, it was 0.71. So we've got a point that's, more or less here. At pi over 3, it was 0.87. So we've got one that's more or less right here. And then at pi over 2, it was actually 1. And then it starts to go backwards, right? So we have at 2 pi over 3, 3 pi over 4, 5 pi over 6, and then pi. And now I will tell you, I'm not an artist. I don't claim to be. I don't really expect you all to be either, because I can already tell this is kind of a little skewed. These should have the same y value. But I think you'll get the overall picture. So going the other way, remember when we move into quadrant 3 and 4, that we have just kind of the reversed values, negative. So here we have this is 7 pi over 6, has a value of negative 1/2. Then our next unit is negative 0.71, negative 0.87. And then finally at 3/2 pi, it's negative 1. Then it will start climbing back out, negative 0.87, negative 0.71, negative 1/2, and then finally 0 at 2 pi. So you can kind of see the shape that's taking place here. I mean, at least we have sort of some dots, if you will. So the question becomes, how do we fill them in? Well, from looking at the unit circle that the value of sine between 0 and pi doesn't bounce around or do something weird. It just continuously moves from 0 to 1. So there isn't some kind of weird jiggling going on between these points. They simply move from one to the next, kind of like a connect the dots sort of exercise. So if we start to basically do that in a smooth fashion, you get something that kind of starts to look like this this humped structure. Now again, I am not a great artist, but this has all of the classic features that we're looking for in a graph. It has the x-axis is labeled, at least enough to be able to figure out what's going on. The y-axis is labeled, and we have the right shape for the graph that has all of the sort of intermediate points. We've connected the dots. So the question then becomes, what happens next? If we kept going to the right or to the left, what happens there? Well, if you go to the left, it's going to start becoming negative. And if you go to the right, it's going to go back up and be positive. So these shapes repeat. They repeat. And I think we're getting just a little bit long here on the video, so I'm going to stop right there with that graph, and then we'll pick this up. I'll probably even use the same page in the next video. So we will see you shortly.